Section 6.4 is on page 407, talks about exponential and logarithmic equations. So here's where we're going to deal with equations and solve, and that's pretty much what we need in the next section to solve all of these applications. We already know about the definition. Log base A, this looks like B, so be it. Log base B of x equals y means if and only if x equal b to the y. So this solves, again, not saying b is bigger than 0 and all of these things. Say they're satisfying those variables right there. That's the definition. That solves anything. We have two shortcuts. I like to call them shortcuts. Other teachers don't like that, but I'm the teacher, they're not in this class. So what are the shortcuts? Shortcut 1, assuming you're dealing with an exponential function, only an exponential function, and assuming if you're taking the log of a quantity, that quantity slash argument is satisfied, positive, bigger than 0. If I get two logs with the same base to equal, that automatically means those are equal. And if I deal with two exponentials with the same base equaling, the powers must be equal, and I could show you that really quick. If you say, so for one, if you say log base b of x equal log base b of y, if I wanted to solve that, wouldn't you make this a power? Those under each other, and those under each other, and there it is. And if you take the second shortcut, okay, stuck on that. If you take the second shortcut, if you happen to say that b to the x equal b to the y, now if I transform that to log form, that is, if I log both sides, what base should I use to eliminate the log? Well, the exponential b, those will undo each other, and those will undo each other, and that's the second case. Easy to derive, you really don't have to derive it, but there it is. So, based on that, I could use logs, and I could use those shortcuts. If I'm allowed to use a calculator, it wouldn't matter. If I'm not allowed to use a calculator, then I should aim for those first. Well, let's see. I'm glancing at this problem and thinking, alright, that's an exponential equation. I see 25 and I see 125, and I know both of those can be written as an exponential with a base of 5. So I could say this is 1 over 5 raised to a power, and I could say this is 5 raised to a power. And how does that work? Well, I could say this is 5 cubed, and this is 5 squared. So here I'm aiming for the second. I'm going to call this the first, and I'm going to call this the second, and I'm going to refer to those as shortcuts. And how that works, I'll say, well, let's see. In this case, I'm going to move this up, that is 5 to the negative 3, and I'm going to multiply those powers, properties of exponents, 2 times the quantity 5x minus 3. 2 times 5x is 10x, and 2 times negative 3 is a negative 6. And now, this satisfies the second shortcut. That is, the bases are the same. Automatically, I just read the powers and proceed. I would say negative 3 must equal the 10x minus 6. Add 6 to both sides. And x would be 3 divided by 10. Right on. And there it is. So, I glance at a problem. First thing come to my mind, look at those and see. I could write any number as an exponential. Any number, 81. Even 5. I could write 5 as 5 to the first power. That's exponential. The question is, can I make those the same? Well, I know if I break 81, that is really 3 to the 4th power. And I am aware, except this one is already in exponential form. 27 is 3 cubed, and the property of exponents, right? if you have a to the n raised to the m, you end up multiplying those. So I need to multiply those. That will be 3. 3 times the quantity 6x minus 2, you distribute, that will be 18x minus 6. And once the bases are the same, automatically you set the powers are equal, and you solve your problem. Add 6 to both sides. And if I divide by 18, 10 over 18, if I reduce, that's 5 over 9. And there it is. And that's how we solve all of those. Well, the same deal, as long as I can make the base the same. What if I can't make the base the same? Well, guess what? This solves anything. It's just longer. A bit longer. So, if I look at number 9, at 10, I'm looking at this and I'm thinking, alright, well, the base. There's a base, there's a base. Yep, I think I could do that. I could write that as 3 squared. That's what 9 is. And I can write that as 3 cubed. So here I gotta distribute those. That's gonna be 3 to the 2x plus 4 equal. And if I move this up, doesn't that become 3 to the negative 1? Negative 3? You have a couple of options here actually. But let's stick with this. 3 to the 2x plus 4 equals 3. And if you multiply those, wouldn't that be a negative 3 plus 3x? And now that the bases are the same, I'll set those powers equal. I'll say 2x plus 4 by the second shortcut. Now I do want to show something really quick. You're not really reinventing anything by doing this, in case you're wondering. If I log both sides, and what base should I use to eliminate the exponential? Well, a base of 3. That will undo, and it's right there. So it's not something you're reinventing. We already know that. Just you haven't seen it in this form. That's about it. So if I go ahead and solve, I will get x to equal a 7. And there it is. And if I look at the last problem, can I make those bases the same? Well, I can't make 32 into a 4, because 4 raised to a power 4 to the 1, 4 squared, 16, 4 cubed. So, but I can make the base a 2. That's the common ground between those two, because they're both binary. And this is 2 to the 5th. And this would be, you multiply those, that is 2 to the 2x plus 4 equal. And if you move this up, that becomes 2 to the negative 5th power raised to the negative 2x plus 3. And for me to be able to use the second shortcut, the bases must be the same. If I multiply those, that would be 10x minus 15. That indicates that 2x plus 4 equals 10x minus 15. 8x equals, what is that, 19? Divide by 8, so x is 19 divided by 8. And that's pretty much it. It looks a lot more challenging than it actually works out. When I get to number 22, well, what if the bases don't match? Glad you asked that. Here it is. Now, I need to make those exponentials. There are numbers floating around. I eliminate those, meaning I isolate the exponential function by itself. If I add 1 to both sides, that's 24. And if I divide by 4 both sides, that's 24 over 4. I'm getting 10 to the x equals 6. There's no way I could write a 10 into an exponential with a base of 6, and there's no way I could write a 6 into an exponential with a base of 10. So there's no need for me to even attempt the shortcut. The shortcut doesn't work, but the definition does. If the shortcut doesn't work, I'm looking at an exponential function. If I can't solve it, I will transform the exponential to a log. How do you do that? Well, you log both sides. What base should I use if I'm going to use a calculator? I should use either a base 10 or a base e. Here, there is a 10. That's good news. So, I could use base 10 both sides, and those undo each other, and x would be the log of 6. What happened to the 10? We agreed if I don't write a base, that means the base is 10. And how would you get that answer? They say round nearest hundredth. Alright, well, here's my magic tool. And if I take the log of 6, 0.778 hundredth, so 0.79. There we go. And just to demonstrate, if I look at the original equation, if I take 4 parentheses 10 raised to the 0.79 minus 1, I'm going to get a number less than 23 or above 23 depending whether I round it down or up. So if I hit equal 23.6, do you remember the answer was 0.78 and a number we rounded up? It was, right? 0.77. Oh, I'm sorry. So that should be 78. My mistake. I'm sorry. So if I go back to this equation and I fix, whoops, there. I fix that to 78. 23.1, again, it depends how many times you round. If I was to take 0.77, right? I need more numbers for it to work. So, if you take out the number to more accurate, oh, come on. If I take more accurate numbers, 0.77815, 77815. Notice what happened if I use that. If I go ahead to the original equation, and if I am to be more specific, that is, more accurate, 0.7815, guess what? Now I'm going to get closer to 23, 22.999. If I take more accuracy, I'll get, as long as you're rounding, you're never going to get the whole number. You're going to get a rounding of it. Alright? So that's something that happens. Looking at 24, I see the same thing. I say, okay, well, I see an exponential. Let me aim for the shortcut. We always do. So, move the 5 over. That's 18 equal 2 into 1 over 10 raised to the x. Divide by 2, 9 equal, and if I move this up, I should have did that here. I'm going to have to move that up, right? And that becomes 10 to the negative 1. So if you divide by 2 both sides, and that will be 10 to the negative x, we have a problem. Again, 9 and 10, I can't find common base to make them identical. So obviously I'm going to log both sides with base of 10. The right side, the log base of 10 will undo that. And x would be what? Negative log base 10 of 9. And if I plug this in my calculator, I can get an answer. Here, they only want us to round to 2 decimals. So if I take negative log of 9, I'll get a negative 0.95. A negative 0.95. So I could always check my work by plugging 0.95 for x and do the right. I should get a number very close to 13. And here's the worst case scenario. I glance at a problem and I say, okay, well, this is exponential. Let me isolate an exponential by itself. If I move that to the right, it becomes a positive. And then I realize there's no way I could write 3/5 as a 7, because 3/5 is 0.6. So what I do, I'm going to log both sides. Do you see there's no 10 in there? So you have two options. Since I'm going to log both sides and use logs, to save myself time, either I use ln or log base 10. It doesn't matter. One of the properties of logs, third law, I could move this up front. That makes this x times natural log of 3/5 equaling 1 minus x times natural log of 7. Remember, these are numbers. Get rid of parentheses. if I distribute that n natural log of 7 minus, this is really natural log of 7x. Now I'm going to get the x's together. You know what? I'm going to write it the other way. Normally we don't do that, but it kind of looks like it's the natural log of 7x. You might mix that. I'm going to move all the terms with an x to one side. So move this to the left. That will be x natural log of 3/5 plus x natural log of 7 equal natural log of 7. Alright, and now what? Now that they both have an x, I factor that out. I'll have a natural log of 3/5 plus natural log of 7. Remember that was on exam 1. I know you forget so quickly. Not logs, but the same idea. Natural log of 7 plus 1c. And what would x equal? Wouldn't that be natural log of 7 divided by all of this mess? Now, how would you input that in a calculator? Well, this is the exact answer. If I'm not allowed a calculator, that's what I'll do, but I am allowed a calculator. So what would I do with that? Well, I'll take parentheses, natural log of 7 divided by natural log of 3/5 plus natural log of 7. 1.36. 1.36, and that's sufficient. That's about it. Now, I would like to take another problem and do the same thing. Same deal. This is an exponential. What I'll do, I'll isolate the exponential by itself. Why do I do that? Because that's how I solve any math equation. To solve any equation in math, isolate the name by itself. If you have a radical equation, isolate the radical on one side, everything else on the other side. If you have a log equation, isolate the log on one side, everything else on the other side. Exponential, radical, you name it, polynomial. Here, again, there's no way I could make the bases the same. That's not possible. So I'm going to log both sides. Since neither base is 10 or e, which my calculator could read, what I'm going to do in this case, I'm going to use log base 10. Last time I used log base. Again, the only reason I like natural log because it's 2 letters instead of 3. But you could use, just to demonstrate, you could say I'm going to log both sides with base 10, not a problem. Properties of logs. This would be x, the log of 5/4. This will be 3 minus x, the log of 5. If you clear the parentheses, and again, get all the x's on one side, everything else on the other side. And factor an x out. And x would be 3 times the log of 5 divided by the log of 5/4 plus the log of 5. And if I want to plug that in my calculator, I could save a bit more space. Okay, doesn't want to do that. I insist. And I'm going to draw that bigger. So if I divide both sides by this parentheses, x would be 3 the log of 5 divided by the log of 5/4 plus the log of 5. And if I plug this in my calculator, and here it is again, I'm going to take parentheses 3 times the log of 5 divided by the log of 5 divided by 4 plus the log of 5. 2.63. And that's all I need. and I'll continue this on the next video.